Hello, students. Well, I like to record an extra supplemental video on this characteristic polynomial and Cayley-Hamilton theorem. Especially, I want to sort of show you the proof of Cayley-Hamilton's theorem using this adjugate matrix that we defined in class. Okay, so this is there's no one here right now, but it's just me talking to myself. So maybe this is like an experiment to see if you are able to just watch a video on a topic to see, if you can learn from it. Okay, so here we go. So I like to just review this very briefly. In the last lecture, we talked about this idea of a characteristic polynomial. And now Cayley-Hamilton is saying putting this matrix A into the characteristic polynomial, we always get the zero matrix. So let's start with that. Okay. So let's first talk about this. Let's define this characteristic polynomial again. Let's see. All right. Come on, Ben. Characteristic polynomial. Okay. So suppose you have a square matrix A. So let A be an n by n matrix. Okay. Its characteristic polynomial, characteristic polynomial is defined by this P sub A of T. Sometimes people write chi or C of A, just a name for this polynomial. It is equal to the determinant of Ti, so this I right here is the n by n identity matrix, minus this matrix A, okay? So if you calculate Ti minus A, this is gonna be a matrix, and then you calculate its determinant. Because of this T, you're gonna get a polynomial in T. Now, a note is that in some literature, sometimes we define this as determinant of A minus Ti. Well, most of the time, it doesn't really matter, except that the leading term will have a plus or minus sign. But if you define it like this, the leading term is always going to be T to the n, and then plus or minus some coefficients, dot, 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 dot. Okay. That is to say, the characteristic polynomial is always going to be a degree n polynomial in T, where the leading coefficient is 1. If you define it using the orange way over here, then the leading coefficient could be plus 1 or minus 1, depending on the size n. So there's an advantage in defining it this way. So the leading coefficient is always 1, okay? So a remark that we will make is that the degree of PA of T is always n, which is equal to the size of the matrix A, okay? Well, the order, right? How many rows or how many columns of this square matrix, okay? And if defined in this way, PA of T equals to determinant of TIN minus A, like this, and not the orange way, then the leading coefficient, the leading term, meaning that the term with the highest power, is always T to the n. Okay, so this is a characteristic polynomial. Now, for every square matrix, you can always compute this thing right here. So, for example, let's say we have this matrix A. Let's just do a small matrix 3, 1, 2, 4, like this. Its characteristic polynomial PA of T is the determinant of T times the identity matrix, the 2 by 2 identity matrix, minus the matrix A, okay? So that will be determinant of T0, 0, T minus this matrix A, 3, 1, 2, 4, and we've got to calculate the determinant of this difference, right? So that will be the determinant of t minus 3, negative 1, negative 2, t minus 4, and lo and behold, if we calculate this, t minus 3 times t minus 4 minus 1 times minus 2, that's 2. This is equal to t squared minus 7t plus 10, right? And so here, this is a degree 2 polynomial, and the leading term is t squared. Okay, so this is the characteristic polynomial of this matrix A. Now, a remark is that this polynomial later, we're gonna use it again. So don't worry that this is a one-time thing. Don't you ever worry about that. We will see this later when we discuss this idea of eigenvalues and eigenvectors of the matrix A. So this is very important concept. Okay, so we will revisit for sure. Revisit this characteristic polynomial. Characteristic polynomial when we study this idea of eigenvalues and eigenvectors. And okay, so they'll play a central role. Okay, but for now, what we'd like to discuss is a magical theorem by name of Cayley-Hamilton. It says that if you calculated the characteristic polynomial and you put the matrix A into this polynomial, then you always get the zero matrix, right? So that's what we want to discuss. Now, before we do that, I just want to make a remark. If you have a polynomial, if f of t is a polynomial, then what does it mean to plug in the square matrix? Let's say, you know, f of t is equal to something like, I don't know, it could have you have a leading coefficient that is not 1, say 3t to the 5th minus 2t to the 4th plus 3t squared minus 7, right? This is a polynomial, okay? And A is any matrix, any square matrix rather. Then f of A, okay, plug A into this square matrix, it really is just this calculation of 3a to the 5th minus 2a to the 4th plus 3a squared. Now here, the constant term, what do you do with the constant term is just 7 times the identity matrix, okay? Because of course, these are all matrices, you cannot subtract a number. So if it's constant, then you scale it by the identity matrix of the curse of whatever size we need, all right? And these powers of this A really just means multiply this matrix that many times. So a to the 5th is a times a times a times a times a, 5 times, right? Okay. So what does Cayley-Hamilton theorem say? So theorem Cayley-Hamilton, right? It says if PA of T is the characteristic polynomial of A, then plug A into the polynomial, characteristic polynomial, you get the zero matrix. If PA of T, I will define it as again, determinant of Ti minus A is the Car-Poly characteristic polynomial of matrix A, then PA of A is always the zero matrix. That is kind of interesting, and somehow that this matrix A is the polynomial root to this polynomial, right? So it's a very curious result. Okay, that's kind of profound, and we'll see why a little bit. Okay, so for example, just to illustrate this just once more, Earlier, in this blue example, for the matrix 3, 1, 2, 4, we calculated the characteristic polynomial to be t squared minus 7t plus 10, right? So let's actually plug this matrix A into its characteristic polynomial. Now we're not plugging A into any polynomial. We're plugging into its characteristic polynomial, right? So let's see what happens. Okay, then PA of A is equal to A squared minus 7A plus 10I. Let's actually calculate this to see if it agrees with Cayley-Hamilton, all right? So A squared is A times A, right? So squaring A, so 3124 times 3124. Let's see what this is, right? So this is 9 plus 2, so 11. 3 plus 4, that's 7. 6 plus 8, that's 14. 2 plus 16, that's 18. All right, so this is A squared. All right. And 7A, 7A is multiply this matrix by 7. So we'll do that. That's 21, 7, 14, 28. And 10I is the matrix 10, 0, 0, 10. Right? That's 10 times the identity matrix. Right? And so if I do A squared minus 7A plus 10I, let's see what we get. All right, that's 11, 7, 14, 18 minus 21, 7, 14, 28. These are just some crazy numbers, right? Plus 10, 0, 0, 10. Let's see what we get. 10 minus 21, sorry, 11 minus 21 plus 10. So the top left entry, 11 minus 21 plus 10, that is 0. 7 minus 7 plus 0, that's 0. 14 minus 14 plus 0, that's 0. 18 minus 28 plus 10, that's also 0. Wow. Okay, that is the 0 matrix. So here, the 0, this is the 0 matrix. The n by n 0 matrix. So it's not the number 0, okay? It is the n by n 0 by 0 matrix. All right, does that make sense? All right, pretending you're there. All right, so this is pretty cool, right? Now, of course, now we know the what. We want to know why. But before we see the why, let's see how we can use it. So there are several applications of this Cayley-Hamilton theorem. First of all, what this is saying is this thing. So notice over here, this relation, in this particular example, we're showing the blue example, we can rewrite A squared, we'll say, since A squared minus 7A plus 10I is equal to the 0 matrix by Cayley-Hamilton. Of course, we also calculated it, but we didn't need to do that, right? We know it's true by Cayley-Hamilton. This implies that we can write A squared is equal to 7 times A minus 10I. Now let's stare at this for a moment. What is the significance of this expression? That A squared is 7A minus 10I. A squared is a number times A plus a number times I. If we use a term that we learned in previous weeks, is that A squared is a linear combination of A and I. So, this is saying A squared is a linear combination of A and I. So this is the main corollary of Cayley-Hamilton. Because the characteristic polynomial is always a degree n polynomial when A is an n by n matrix. So here A is n by n. That means the nth power of A is always a linear combination of the lesser powers of A, including the identity matrix. The identity matrix can be thought as the 0th power of A. All right. So a corollary is this. A corollary of Cayley-Hamilton. Kind of an important corollary. If A is an n by n matrix, then A to the n, the power, A to the nth power, okay, very specific. If this is 10 by 10 matrix, then A to the 10 power, A to the n is a linear combination of A to the n minus 1, A to the n minus 2, to A down to the identity matrix, which can be thought as A to the 0th power, if you will. Okay. So why? This is because of Cayley-Hamilton, right? Let's prove it. A short proof. Okay. If we believe Cayley-Hamilton, PA of A is equal to the 0 matrix. But PA of A is equal to some A to the nth power plus some coefficient. So we don't know what the coefficient is. So let's say Cn minus 1, A to the n minus 1 plus plus C1A plus C0I, like that, right? Now, it's very important to know that this leading term, the coefficient is always 1, right? That is a property of characters of polynomial. Later, much like our obsession with determinants, one could obsess over this characters of polynomial as well. There's a lot of things to say about it, of course. And just like the determinant, it's also defined out of the determinant, so itself is also a very interesting object. But nonetheless, this leading coefficient right here is always a 1 if we define it using determinant of ti minus a. If you do it this orange way, determinant a minus ti, then you get a plus or minus sign, okay? But here, this is always plus 1. Okay, so by Cayley-Hamilton, PA of A is equal to 0, but PA of A equals this thing, which equal to 0, okay, 0 n by n matrix, right? Then I can solve for A to the n, right? So this implies A to the n is just equal to negative Cn minus 1, an minus 1, minus Cn minus 2, let's say there's a Cn minus 2 term, A to the n minus 2 term, power, minus minus C1, A minus C0I, right? And what does that mean? Look, this means that this A to the n power matrix is just some number, some weird number, times A to the n minus 1, plus some weird number, times A to the n minus 2, blah, 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 to I. That is to say, an is a linear combination of an minus 1, an minus 2, to the identity matrix, okay? Wow. All right, but now the idea of a linear combination is that information regarding A to the n is really just information about these things that make up this combination. That is to say, if I want to know A to the n, all I need to know is what these smaller powers of these matrices are. Then I can get A to the n, right? That's one way to think about this. So, for example, an application of this is that we can use this to calculate powers of matrices in a very curious way. For example, in this blue example, we found the characteristic polynomial of the square matrix is t squared minus 7t plus 10, right? And we got down to this relation, a squared is equal to 7a minus 10i by Cayley-Hamilton. We can use this to calculate, say, for example, the 4th power of a. Let me show you how. So example, can use Cayley-Hamilton to compute matrix powers. Now, generally, matrix powers, you have to, if a matrix is large, then there's a lot of calculation to be carried out. You have to keep multiplying to itself. It gets kind of complicated. But here's a curious way of finding matrix powers. So, for example, if A is the same matrix as before, 3, 1, 2, 4, we found earlier that the characteristic polynomial was t squared, minus 10, minus 7t plus 10, right? So by Cayley-Hamilton, a squared minus 7a plus 10i is 0. So we know that here is a matrix power that we know, a squared. Instead of calculating a squared, we don't need to square this matrix now, right? Instead, we could do it backwards. Earlier, we calculated a squared. Now, we can just say a squared is just 7 times a minus 10i. How easy, right? But we can do more, of course. What if I want a to the, say, 4th power? Well, a to the 4th, as you can guess, is a squared squared, right? A squared times a squared, so a squared squared. But a squared itself is 7a minus 10i, quantity squared. And if I square this, now usually when I multiply matrices, I need to watch out for commutativity, but identity matrix commutes with a's. So this is just, this is just 49a squared minus 140a plus 100i quantity squared, right? And right now it looks kind of incredulous, but all I did is not quantity squared. I already squared this, right? I squared this to get this, all right? And you said, okay, so what? I still don't know what a squared is. Well, I can reduce a squared once more because a squared is 7a minus 10i. So this is 49, 7a minus 10i minus 140a, right? Plus 100i. And there we go. So what is this? Let's see. 7 times 49. 63, 6, 28 plus 6, 28 plus 6 is 34. Okay, so this is 343a minus 490i minus 140a plus 100i. Okay, let's see what we get. And I gotta do some subtraction here. So 343a minus 140a, that is 203a, and then minus plus this identity, we get minus 390i. Well, there we go. This is saying that a to the 4th itself is also a linear combination of a and I, and here it is. Okay, which is kind of curious, and we might not even believe that this is true, but I'll leave you to verify this. Okay, so check this. Perhaps I did it right, perhaps I did it wrong, but check this. Okay, so this is kind of neat, right? We can use Cayley-Hamilton to find powers, and in fact, these matrix powers will also be linear combinations of lesser powers of n. That is to say, we have another corollary by this example. Because we could keep reducing this using Cayley-Hamilton. If A is an n by n matrix, then any power a to the k with k greater than or equal to n, just like this, 4 is greater than or equal to 2, is a linear combination of a to the n minus 1, a to the n minus 2, dot, 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 a, and an identity matrix. That is to say, any higher power, n or greater, you can always write it as a linear combination, okay, of powers of a that are powers less than or equal to n minus 1. So starting from identity, which is a 0 power, 1 power, 2 power, all the way to the n minus 1 power. And so this is because we can just keep reducing, so that we always get down to just these lesser powers. This is pretty cool, right? All right. But wait, there is more. In fact, if A is further invertible, and this is a very classic important fact, then this inverse of a matrix can also be written as a linear combination of powers of something. Well, let's see what that is. Okay. Now, if A is invertible, okay, if A is invertible, then we can also write a inverse as a linear combination of something. Okay, let's see what that would be. All right. So by Cayley-Hamilton, we know PA of A is equal to the 0 matrix, right? Where PA is this characteristic polynomial. So this is saying that some A to the n, so let's say A is n by n, A to the n plus some coefficient, Cn minus 1, A to the n minus 1 plus Cn minus 2, A n minus 2 plus dot, 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 plus C1A plus C0I is equal to the 0 matrix. Now, there is something important about this C0 number. So what is the C0 number? Well, this is the constant term of the polynomial, right? So we claim that this constant term is going to be not 0 when A is invertible. In fact, we'll see what this constant term is. Notice that if P is a characteristic polynomial of A, so it's determinant of Ti minus A, like this. What happens if I plug in 0? Well, firstly, this is a polynomial of the form t to the n plus cn minus 1, t to the n minus 1 plus dot, 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 plus c1t plus c0, right? If I plug in 0, this is calculating determinant of minus a, right? And on the right-hand side over here, this is just the number c0. And if a is invertible, determinant of minus a, so if a is invertible, then minus a is also invertible. So c0 is not going to be 0 when a is invertible. In fact, you can calculate determinant of minus a because of multilinearity. Now, minus a meaning scale each row by minus 1. So if there are n rows, each of the minus 1 comes out. So this is minus 1 to the nth power times the determinant of a. This is equal to c0. And so if a is invertible, the c0 constant is not equal to 0 because it is equal to some plus or minus of determinant of a, which is not 0. So when a is invertible, this last term c0 is not 0. That's an important observation. Now, how can we use this to write down the inverse as a linear combination of something? Well, look at this. If I take the Cayley-Hamilton expression over here, a to the n plus cn minus 1, a to the n minus 1, plus dot, 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 plus c1a plus c0i equal to 0. What I could do is I could factor an a in these previous part. So I'm going to factor an a out, okay? So we get a times an minus 1, yes, plus cn minus 1, an minus 2, plus dot, 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 plus c1i, because I factor an a out, plus c0i is equal to the 0 matrix. That is to say, a times, if I move the c0i over, times this whole nonsense, is equal to negative c0i. Now, why am I writing it like this? Because if I now divide by negative c0, which is a non-zero number that we can divide, I get a times some matrix is equal to identity, right? Which is kind of interesting. Why is this interesting? Because now this gives us another way of writing out A inverse, right? Because here we have A times this crazy nonsense is equal to I. We can actually write A inverse as a linear combination of the powers of A starting from n minus 1 to I, right? So this shows A inverse equals minus 1 C0 times an minus 1 plus cn minus 1, an minus 2 plus dot, 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 plus c1i. Yeah, because A times something equal to identity matrix, meaning that the something is A inverse, right? So there we go. So a corollary is this. The corollary is that A inverse is also a linear combination of powers of A up to n minus 1 power. Which is also kind of curious and interesting, right? Corollary. If A n by n is invertible, then A inverse is a linear combination of an minus 1, an minus 2, dot, 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 a to I, okay? In particular, you can calculate its inverse using this formula over here, all right? So that is kind of neat. So you can try to use this to calculate A inverse, all right? Well, actually, let's maybe try, right? Let's maybe try. Let's use this example. For example, let's look at this matrix A from previous. Okay, so in this blue example, our matrix A 3, 1, 2, 4, right? 3, 1, 2, 4. Let's use the same matrix 3, 1, 2, 4. Let's use this weird method to calculate A inverse, shall we? All right. So here we saw the characters of polynomial. It was t squared. Oh yeah, I forgot already. T squared minus 7t plus 10. Okay. So by Cayley-Hamilton, we have A squared minus 7a plus 10i is equal to the 0 matrix. If I factor an a out, so I get a times a minus 7i plus 10i, that is equal to 0, which means that the inverse is equal to 1/10 of a minus 7i. Okay, because, oh, sorry, minus 1/10, because, right, if I move this 10, minus 10 over, right? Okay, let's just write out that step. A times a minus 7i is equal to negative 10i, right? So if I were to divide by minus 10, then I get A inverse because that is the matrix. When multiplied to A, I get identity. Well, let's check it out. So that is minus 1/10 of the matrix A, 3, 1, 2, 4, minus 7, 0, 0, 7, right? That is 7i. Let's see what this is. 3 minus 7, that is negative 4. 1 minus 0, that's 1. 2 minus 0, that's 2. 4 minus 7, that is negative 3. So A inverse is this matrix, 4 over 10, okay, sure, minus 1 over 10, 2 over 10, minus 2 over 10, and 3 over 10, right? Okay, kind of bizarre. Well, let's check. We know how to calculate inverses in so many ways now. Because it's a 2 by 2, we can just calculate it directly. The determinant is 3 times 4, 12 minus 2. Oh, that's the 1 over 10. Interesting. And let's see. Swap main diagonal 4, 3, negate off diagonal. So this is the adjugate matrix, right? And let's see what this is. This is 1/10 of 4, negative 1, minus 2, 3. Is that the same thing? Yes, it is, right? The next sign all makes sense. So they are the same. Wow. So Cayley-Hamilton itself is quite useful, all right? It is able to write higher powers of A as some linear combination of lesser powers of A. The lesser powers being starting from identity to the n-1 power if A is n-1, if A is n by n. And similarly, when A is invertible, this A can also be, the inverse can also be written as this power of these, a linear combination of the lesser powers of A. Okay, so this is pretty neat, right? So that's sort of one of the main uses of Cayley-Hamilton is to establish some facts about powers and inverses of A as linear combination of lesser powers. Of course, there's more uses to this, but there's at least some taste. So now I like to prove Cayley-Hamilton because now we saw the what is Cayley-Hamilton, what is the characteristic polynomial. We see the what can we do with it, right? Some applications of this. And now we need to know the why. Why is Cayley-Hamilton theorem true? And I mentioned in class the easiest, sort of the most elementary way, meaning without using even more sophisticated mathematics, is to use this adjugate matrix. Okay, so the book teaches you the adjugate matrix, and I showed you what the adjugate matrix is. We're going to use the property of the adjugate matrix to prove Cayley-Hamilton theorem. Okay, so that is to me perhaps the most important usage of this adjugate matrix is to be able to prove Cayley-Hamilton, which itself is a very big result in linear algebra. So what was the adjugate matrix? Remember, it was a matrix defined using these cofactors similar to Laplace expansion, right? But more importantly, is a matrix defined out of any square matrix where the product is always determinant times the identity matrix. That's the only property that we really need to know, plus how we calculate this adjugate matrix. So let us prove Cayley-Hamilton. Now, of course, to prove Cayley-Hamilton, I need to show you the general n by n case, but that's just gonna makes too many indices, then just too abstract. So I'm gonna show you the 4 by 4 case. And once you see how the 4 by 4 case works, for example, then you can see other sizes. I choose 4 because there's enough terms to play around, and then you'll see how to generalize the n by n case. So it's exactly the same idea. Okay, so I'm gonna just show you the 4 by 4 case. You can do it the n by n case once you understand this 4 by 4 case. Okay. 4 is just a random big enough number. 2 is too small. 3 is small enough. 2 kind of so too small, but let's just do 4. Okay, we'll see. Okay, so all I need to know is recall the adjugate matrix. Okay, the adjugate matrix of M is a matrix such that when M, this matrix M, multiplied to the adjugate of M, this is always equal to the determinant of M times the identity matrix. Okay, so determinant M is just a number times identity matrix. Okay, so this is the main adjugate property of this adjugate matrix. And this adjugate matrix, please review from lecture to see how it was defined, okay? But every square matrix, you can calculate its adjugate matrix. Now, what is it that we want to prove the 4x4 Cayley-Hamilton? Okay, so suppose I have a matrix A that is 4x4, okay? With characteristic polynomial, let's say its characteristic polynomial PA of T is equal to determinant of Ti minus A, okay? Now, we just saw that this is gonna be a degree n polynomial if A is n by n, so this is a degree 4 polynomial, so this degree 4 polynomial looks something like this. T to the fourth plus C3 T cubed plus C2 T squared plus C1T plus C0, right? It is a degree 4 polynomial. What is it that we wish to show? We wish to show that A to the fourth, right, when we plug it in, plus C3A to the cube plus C2A squared plus C1A plus C0I is the zero matrix. So that's what we want to show. We want to show that this whole thing is equal to the zero matrix. Okay. Sometimes I draw a double underline to emphasize those are matrices. The C's are just numbers, scalars. So this is what we want to show if I want to prove Cayley-Hamilton for 4x4 case. Of course, you can imagine this 4 is just some n, some arbitrary integer n, positive integer n. Okay, now how on earth are we going to accomplish this? Well, first, I'm going to define or consider the adjugate matrix of Ti minus A. So let us denote the adjugate matrix, okay, of Ti minus A as the matrix B. All right. Now, what will we know about this matrix B? Well, because it's the adjugate of some matrix of Ti minus A, this means by this adjugate relation, Ti minus A, this matrix, times B, the adjugate of Ti minus A, is going to equal to the determinant of this matrix, Ti minus A, times the identity matrix, okay, scaling the identity matrix. Well, the determinant of Ti minus A, that is the characteristic polynomial, so this is equal to the characteristic polynomial times the identity matrix. Now notice this expression has a variable T's everywhere. In fact, this matrix B itself has entries with a bunch of T's in it. This B is a 4x4 matrix because it's the adjugate of some 4x4 matrix with T's in its entries. In fact, that is to say, to be more precise, where each entry is a polynomial in T. Okay. Furthermore, because how adjugate matrix is calculated, it is these cofactors, right? It's each entry of B is the computation of removing a row and column from this matrix Ti minus A and calculate the determinant of its 3x3 submatrix. Each entry is not just a polynomial in T, it is of degree at most 3. Okay, so the degree is always at most 3. So even though this is a 4x4, when we calculate the adjugate, we always cover a row and a column. So at most there is only T cubed that shows up in each entry. So this is something that you have to think about. Maybe draw it out. But this is important. So what does that mean? Now, since B has coefficients, has entries that are polynomials in T, we can write this as, we can factor this matrix as something like T cubed B, let's call this B3, plus T squared B2, plus T B1, plus T0, T to the 0 power, which is 1, times B to the 0, B0, where BIs are some constant matrices. Constant 4x4 matrices, meaning there is no T's. Okay, so I can, because the terms in B are polynomials in T, right? So I can separate them. For example, let's say we have a matrix T squared plus T, T cubed, negative T, then you can think of this as T cubed times 0, 0, 1, 0, right? Plus T squared 1, 0, 0, 0, plus T 1, 1, 0, negative 1, right? I can factor these like this. Okay, so generally we have this something like this. So because B, each entry is a polynomial in T of degree at most 3, we can write it like this. Okay, and now comes the game. The game is matching terms. We're gonna stare at this equal to this, and we're going to match powers in T, a classic trick in algebra and calculus, or in math in general. So let's see what we get. Let's do it. If I write all of this out, Ti minus a b, okay, equals to the characteristic polynomial of T times I. Let's see what happens if I write everything out. Are you ready? This is going to be something crazy. Ti minus a. Now B is this T cubed B3. Again, I will underline the matrices. And these are, in fact, all going to be constant matrices now. T cubed B3 plus T squared B2 plus T B1 plus B0 is equal to the characteristic polynomial times I. Well, what is a characteristic polynomial? That is this thing times I, right? So each of these is going to get multiplied by I, and I can distribute that. So I'm going to distribute I on it. Oh my goodness. Here it is. So I'm going to take this times I. So this is T4 times I, right? And then C3T cubed times I plus C2T squared times I plus C1T times I should have just written this out much faster, times 0 times I, right? This is the characteristic polynomial T times I, right? Everything, I just distributed everything. Okay, so now we have this new crazy thing. Okay, so what do you say? Good question. Now we're gonna match terms. This is our favorite trick. Match powers in T. This matching powers in T is just important. It's just such a good trick. Such a good trick. Now to appreciate why this trick works, that's a whole nother thing. But the trick works, as you have done it before. For example, when in calculus 2, you probably did something like partial fraction decomposition, and you match powers of T, blah blah blah. You can do it over here as well. Now, I'm not saying this always work 100%. There are very special cases where it doesn't work, but that's only because the number system is not nice. If the number systems are reals, complex, this always work. And so that's what's amazing about this. Okay, and we're dealing only real matrices, maybe later complex matrices. We don't deal with other number systems. So at least not in this class yet. So let's match powers in T. Let's see, what is the highest power in T? Let's see. We have T here, we have T cubed here, so we have T to the fourth, right? So let's see what kind of things we have T to the fourth. Okay, I'll make a table, left-hand side and right-hand side. For the left-hand side, T to the fourth is I times B cubed, sorry, B3, not B cubed, B3. And that's it, there's no T to the fourth. On the right-hand side, we have identity, right? What does that mean? That means B3 is identity, okay? Let's match the T cubed term. The T cubed term comes from here and here on the left-hand side. So that is B2 minus AB3. Okay, kind of bizarre. On the right-hand side, this is just C3I. Okay, let's keep going. T squared term. The T squared comes from here and, here and here, right? Those are the T squared terms. So that is B1 minus AB2. That is equal to T squared on the right-hand side is always easy, C2I. Two more. The T term comes from A times this guy and Ti times this guy. So that is B0 minus A B1. And that is C1I. And finally, the constant term, the ones without T, that is minus A and B0. So on the constant term, we just write 1. So that's minus A times B0. On the right-hand side, that is just C0I. So we match powers in T. So what? Well, so what is this? This part almost looks like a characteristic polynomial, except we don't want I. We want A to the fourth, A cubed, A3, A2, A1, and identity, right? So what I would do is this. For the first one, I'm going to multiply by A to the fourth on the left. Okay, multiply this first equation by A to the fourth on the left. So what do I get? I get A to the fourth B cubed. That is equal to, on left, meaning on the left of both of these sides. Okay, like that. All right, so that's what I'm doing. So I get A to the fourth like that. And then for the next one, I'm going to multiply by A cubed. Okay, so that's A cubed times this. A cubed times, I guess I should have just written it, but I will just write it out over here. So I get A cubed B2 minus A fourth B3. That is equal to C3 A cubed. And then this one we're going to multiply by A2, A squared that is. So I get A squared B1 minus A cubed B2. And that is equal to C2A squared. And I think you see where this is going, times A, like that. And so now if I multiply this by A, I get A B0 minus A squared B1 is equal to C1A. And finally, just don't do anything, minus A B0 is equal to C0I. Okay, so I multiply these powers of some A's, and now I get this. Okay, so let me erase these orange ones. All right. Now, what do we get? Here we have a bunch of things on the left and a bunch of things on the right. So if I add them vertically, let's add them vertically. If I add them vertically, look at what happens. A4 B3 minus A4 B3, that cancels. A3 AQ B2 minus AQ B2, that cancels. A2 B1 minus A2 B1, that cancels. AB0 minus AB0, that cancels. This is what we call a telescoping sum. Right? The telescopes. It's add and minus, add minus, add minus. So the left-hand side is the zero matrix. So here we're doing is add, vertically, right? Now, on the right-hand side, that is just a to the fourth plus C3 a cubed plus C2 a squared plus C1a plus C0i. But what is that? That is a plugging it into the characteristic polynomial. Therefore, the characteristic polynomial plugging in a is indeed a zero matrix. Wow. At least for 4x4, right? But you can imagine this generalizes to higher sizes, right? If it's like, 10 by 10 or n by n, it's just the same thing, you just have to expand this and match terms. A bunch of things are canceled once you adjust it by a power of a, and we got it. And the only property that we use really is the adjugate times this matrix is the determinant of this matrix times identity. That's all we used. And some property of the adjugate so that we know that this B is a n by n matrix with power in polynomial in T in the entries of degree at most n minus 1. That's all we need to use about adjugate matrix. But yet, with this powerful result, with this simple, humble adjugate matrix, we're able to prove this very powerful result called the Cayley-Hamilton theorem. Okay. So this is an experimental supplemental lecture to see if we can learn things. That is an additional video. I don't know. There's no one here. So I'm just talking to myself. So see if you can understand this. And this will be, at least the applications of Cayley-Hamilton and the characters of polynomial will be very important. So at least understand this first page of material. Okay. And try your best to understand why Cayley-Hamilton. Now, if you understood this proof, you'll be among the few people, I would dare say, that knows this proof by heart, knows a proof of Cayley-Hamilton by heart. If you grab a random mathematician and say, you ask them what the Cayley-Hamilton theorem is, they will tell you what it is. Everybody knows its statement because it's such a fundamental fact in linear algebra. But then if you say, prove it, and don't give them a blank paper. Usually people don't remember how it goes, because oftentimes you have to use some other routes talking about this thing called cyclic invariance subspaces, blah blah blah, some advanced concept to prove it, which is fine, which has its own value, learning about this new concept. By the way, in the United States, usually if you go in more math or more engineering or sciences, there is an upper division of linear algebra, and they will teach you a more sophisticated way of proving this fact. Well, I hope, right? Otherwise, you ask for a refund. But right now, we have a down-to-earth classical way of proving this without using too much sophisticated tool besides just algebraic manipulation, matching terms. Okay? All right. Let me know if you have any questions. Of course, in office hours, I can answer questions. Let me end recording.